So we're going to do 1.7, investigating horizontal stretches, compressions, and reflections. So far in this last year and this year, we've done all of the stretches and compressions and the translation shifting left and right, up and down. We focused on vertical stretches and compressions and reflection on the x-axis, but we never looked at a reflection on the y-axis or horizontal stretches or compressions. So that is what the new transformation is this year. And not only will you have to be able to perform this transformation to parabolas, because that's what you started off transforming last year, you're going to have to be able to use these transformations in order to transform absolute values, the y equals square root x graph and the y equals 1 over x graph. So let's take a look at this. It says key concepts here. Now, where do you find your horizontal stretch or compression? Well, this is written as function notation here, and I went over this last time. Y equals, if you have an a in front of your function, so an a in front of your x squared or an a in front of your square root, we know that if a is bigger than 1, then there is a vertical stretch by a factor of a. And if a is between 0 and 1, then it is a vertical compression by a factor of a. And then we also know if a is negative, the graph is reflected on the, and this should say x-axis, so make that correction. It should be, the graph is reflected over the x-axis. So all of your y values become negative. It is a reflection. In the x-axis, it's what turned the parabola upside down, or the absolute value upside down. And if we take a look over here, where we haven't seen a multiplication yet is the multiplication if it was inside of the function. So if we have a multiplication inside the function being multiplied by x, and we're going to call this k. Now, your book starts calling this value k, not to be confused with the k value that comes at the end of your shifting up and down, but I'll get to that later. But if there is a number being multiplied by k inside of the function, so inside of the square root, inside of the absolute value, or inside of the square, the parabola, if k is greater than 1, then this actually works in reverse. It is a horizontal, should say horizontal compression by a factor of 1 over k. If k is in between 0 and 1, then it is a horizontal stretch by a factor of 1 over k. And also, if k is a negative, then it's going to be a reflection on the, this should say y-axis. That's a typo. So we'll change that. That should be a reflection on the y-axis. So, this is me telling you this, but let's actually look at this and see for ourselves why this happens. So if you look at example 1, it says graph the two functions below. So we're dealing with a parabola. So we're going to graph the two functions below plus the function of y equals x squared on the same set of axes. So what I want to do actually is I want to graph y equals x squared. I want to keep this one the same and graph y equals 2x to the power of 2, but please get rid of these x values. And over here, what I want to do is not graph this. What I want to do is graph y equals 1/2 to the power of x, just so you can see what's going on. You'll see it a little better with the half rather than the 3 there. Now, again, also get rid of these x values for now. So let's take a look at this. So the first graph, y equals x squared, I will do that graph in red. We know how to graph a parabola from a window of -2 to 2. And if we plug in -2 here, this will be -2 squared, which is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. And that is y equals x squared. We'll graph that in a second. And that's the table of values for y equals x squared. Now, over here, what we have is y equals, now this is not your a value. That 2 is inside of the bracket all squared. So you have a number inside of the square bracket being multiplied by the x. And we know from experience that anything inside of the bracket with a parabola, for instance, this is our formula in vertex form, anything that is inside, like your h value, anything that is inside your bracket, inside of your square bracket, that affects your x values. Anything outside of the bracket, like your a and your k out here, anything outside of the bracket, that affects your y values somehow, and we saw that from last lesson. But this h inside, that affects your x values. That is what shifts the graph left or right. So with that said and that noted, this 2 is inside of the square bracket. And when it's inside of the square bracket, that should affect your x values, not your y values. So with knowing that, what I'm going to do is I'm going to come up with a table of values, but I'm going to compare this to the original graph, because we should always compare this to the original graph of y equals x squared. Now, since we don't have graphing calculators and we're trying to understand what's happening with the 2 in here, what I'm going to do is I'm going to use my previous knowledge, and I know that my x's are going to be affected, not my y's, because again, it's inside of the bracket, it's inside of the square. So in order to go from this bracket here, in order to go from this function here, y equals x squared, to this, the only difference is the 2 inside of the brackets. So I know that that affects my x values. So in order to transform from here to here, my y values should remain the same. 2, 1, 0, 1, and 4. What should be affected are my x values. And what I'm going to do is I'm going to work in reverse. And I'm going to ask myself, what x value should I plug in here to give me the answer y equals 4? So I start, playing backwards. I start kind of doing things, and I start saying to myself, I start playing with numbers, and I say, you know what? If I plug in an x equals 1, if I plug in an x equals 1 here, 2 times 1 all squared, this is going to be 2 times 1 in the brackets, which is 2 all squared, and that is what will give me 4. So if I plug in x equals 1, that is what will give me 4. And also, if I plug in x equals negative 1, so if I plugged in x equals negative 1, that will be in the bracket 2 times negative 1, which is negative 2 all squared, and negative 2 all squared is also 4. So if I plug in an x equals negative 1, it also gives me 4. So why am I doing this again? Again, I know nothing about this graph, but what I do know is that if something is inside of the bracket, that affects my x values. I have to figure out how this 2 affects my x values. So far, and looking back to my original, my parent function, I know that if my x values are the ones being transformed, my y values should remain the same. So then I start playing with the numbers again, and I start asking myself, what should be plugged in for x in order for me to get a final answer of 1 for y? So what should my input be in order for my output to be 1? So I start working backwards, and I start saying, you know what? If I plug in x equals a half in for x, a half in for x, inside the bracket this will be 2 times a half, which is 1 all squared, and 1 all squared is 1. So if I plug in 0.5 or a half for x, I will get the answer of 1, working backwards. And again, I also notice if I plug in negative a half, so if I plug in negative a half in for x, this is going to be 2 times negative a half, which is negative 1 all squared, and negative 1 all squared is 1. So also if I plug in negative 0.5, that also gives me an answer of 1. And then the easiest, obviously, would be what should I plug in for x in order to get an answer of 0? So what should my input be? Well, my input should be 0, because then I will have 2 times 0, which is 0 all squared, and 0 squared is 0. So when I put an input of 0, I get an output of 0. Again, this will give us a better understanding to what happens to the graph of y equals x squared, because I know for a fact from previous experience, once again, that if there is a number inside of the bracket, inside of the function, and it's being multiplied by x, the things that should change are my x values. Those are the things that should transform, not my y's. And so in order to go from here to here, my y values should stay the same. I worked backwards to figure out what I had to plug in for x in order to get that output, the same output. And if you start noticing the difference between these x values and these x values, what you will notice is that these x values are exactly half of those x values. So with the 2 being inside of here, the x values were cut in half. Those x values are all half of the previous ones. So there's a 2 in front of the x inside of the bracket, but this is a horizontal compression by a factor of a half. So I'll just write that. Horizontal, and it's very important that we write horizontal. This is a horizontal compression by a factor of not 2, but 1 over 2. And that goes back to what we were stating up there. Okay, if x is a number bigger than 1, it was a horizontal compression by a factor of 1 over whatever the k value was. And so, again, I can draw these two things. I'd actually like you to draw these two things here. And how will they look different? Well, obviously that will look like a regular y equals x squared graph. If the graph is compressed horizontally, well, horizontally is this way. If you're compressing the graph horizontally, you're squishing the graph horizontally. That's what the blue graph should look like. It should look squished, the squished version of this horizontally. Okay, so that is that one there. The next one over here, and I'm just going to erase this, and I'm going to do this one here, y equals a half to the power of x. So again, once again, if there is a 2 out in front of the x, if your k value, again, I will explain why they call this k all of a sudden, not to be confused with the k that is your shifting up and down. They do this purposely, and I'll explain to you later on why. But the k value, if it's 2 being multiplied by your x, remember that is actually a horizontal compression by a factor of 1 over 2. So let's take a look at our next one. And our next one here is graphing y equals a half to the power of x. So if I want to graph y equals half to the power of x, again, you know the numbers here are 4, 1, 0, 1, and 4, because that's y equals x squared. And if I want to go straight to here, which is y equals a half, so this is what I want you to graph, y equals a half x squared, sorry. So if I want to do y equals a half x squared, and remember what the 2 did when it was inside. The 2 was a horizontal compression by a factor of 1 over 2. Now, how about when we have this? Y equals a half times x all squared. Again, this half is inside of the function, so what should be happening is my x values, something should happen to my x values. Okay, so if I look at the difference between this formula and this formula, the only difference is that there is a half inside of the bracket. So what I'm going to do is, knowing this and knowing that my x values should change, I'm going to transform this to this. I know that my y values should be the same, 4, 1, 0, 1, and 4. And I'm going to work backwards to figure out what my inputs should be in order to get the same outputs. So what should my input be for x in order to get the answer of 4? And then you start playing around with it, and then you start understanding that it should actually be a 4. When I plug in 4 for x, this will be half of 4, which is 2, and 2 squared is 4. So when I plug in a 4 for x, I get an output of 4 for y. And likewise, if I plug in negative 4 for x, this will be half times negative 4, which is negative 2, and negative 2 all squared is 4. So if I plug in a negative 4 for x, I will also get an answer, an output of 4. And then I start playing around with it again, and I ask myself, what should I plug in for my input in order to get an output of 1? And I play around with the numbers, and I finally find out that I should actually plug in a 2 for x, because half of 2 would be 1, and 1 squared is 1. So if I plug in a 2 for x, I get a 1 for y. And also if I plug in a negative 2 for x, that'll be negative 2 times a half is negative 1. Negative 1 squared is 1. So if I also plug in a negative 1 for x, I will get a 1 for y. And of course, if I plug in a 0 for x, I will get an output of 0. So I also want you to graph this green graph on the same graph and compare it to y equals x squared. Now what is the difference between this and this? Well, the difference is that your y values are the same. Your y values are exactly the same, but it is your x values that have changed. See, your x values, if you compare it from here to here, all of your x values have doubled. So this is actually a horizontal stretch by a factor of not a half, but of 2 over 1. So that actually ends up being a horizontal stretch by a factor of 2. Even though there's a half in there, it is a horizontal stretch by a factor of 2. Again, your graph, the green graph, should look horizontally stretched. So it'll be wider by a factor of 2. Okay, so example 2 says graph the two functions below plus the function y equals the square root of x on the same set of axes. So we're going to do the square root of x and see what happens when we apply the same transformations, which is our h value, or sorry, our k value. And our k value, remember, is not the number that comes after the brackets or after the square or after the square root. It is now called the number that is in front of the x being multiplied by the x. And they've done that purposely so that you understand that all of these variables are interchangeable. So we're calling our k value this year from now on is the number in front of x inside of the function. So I want to do two graphs here. First I'm going to start you off by graphing y equals the square root of x. So the square root of x, remember, the lowest number you can pick is 0. Should be 0, not 1, 0, and no negatives obviously because you can't take the square root of a negative number. But the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, square root of 9 is 3, and the square root of 16 is 4. And remember, we pick perfect squares so that we're able to do whole numbers here. And so this is what the graph looks like for y equals the square root of x. So I'd like you to graph that on there right now. And as you're doing that, we're going to apply these transformations. So the first one I'm going to do, I'm actually going to switch this last one here. But the first transformation we're going to do is, how about if we have y equals half, the square root of half x. So how does that affect our graph? And again, from the last one, we know that if there is a half inside of the function being multiplied by my x values, that is somehow going to transform my x values. This is a transformation that we haven't seen before. So again, my y values from the original graph will not change. Those y values will remain as 1, 2, 3, and 4. It is my x values that will change. And how do my x values change? Well, again, we're still in the preliminary round of figuring out how this affects our graph. So let's work backwards with this equation of y equals the square root of half x. And let's ask ourselves, what should I plug in for x in order to get the output, or y equals 0? And the correct answer would be, I'd have to plug in x equals 0. This would be a half times 0, and we know that underneath the square root, a half times 0 is 0, and the square root of 0 is 0. So I'd have to plug in x equals 0, the input, in order to get the output of 0. And then, what should I plug in for x in order to get an output of 1? And the correct answer is a 2. Because a half times 2 is 1, and the square root of 1 is 1. So I'd have to plug in x equals 2. I'd have to input x equals 2 in order to get the final output, or the y value of 1. And then I ask myself, well, what do I have to do in order to get the output of 2? What should I input into this formula? And the correct answer would be 8. Because half of 8 is 4, and the square root of 4 is 2. So I have to plug in an 8 for x in order to get an output of 2. And then the last one I'll do here is, what do I have to input for x in order to get a y value, or an output of 3? And the correct answer would be 18. Half of 18 is 9, and the square root of 9 gives me that answer of 3. So I have to plug in 18 for x in order to get an output of 3. And of course, I want you to graph this graph in green. I want you to graph this graph on the same set of axes as you have y equals the square root of x. And I want you to relate the two graphs and how they've transformed. Again, this is a transformation that we haven't seen before. But if you take a look at the y values, your y values are exactly the same. The heights are exactly the same. What switches or what transforms are your x values, which makes sense because that half is inside, in front of the x being multiplied by your x. Now, how do they transform the x values? Well, if you take a look at 1 for 1, the first x value is 0, then it's 0. The second x value is 1, and it transforms to 2. The third x value is 4, it transforms to 8. And then 9 transforms to 18. So as you can see, this is a horizontal stretch by a factor of 2. You are doubling all the x values. Even though you see a half there, this is a horizontal stretch by a factor of 2 over 1. Again, this is something we haven't done before. This is the first time we're taking a look at this horizontal stretching and compressions. So it's very important that you understand that a half in front of the x inside is a horizontal stretch by a factor of 2 over 1, which deals with what our number 2 things said at the top there are transformations, whatever k is. And when there's actually a 4 in front of the x, it's actually a horizontal compression by a factor of a quarter or 1 over 4. Okay, so we're going to actually do this last one here. And the last one, this one here, I want to come up with this table of values, but I don't want to come up with the table of values for a third. I'm going to actually change this. And I want to come up with the table of values for y equals negative x. So what happens when there's a negative? Okay? And again, we understand that when you're plugging in these numbers here, they're all relative to y equals the square root of x. So how do you change y equals the square root of x to y equals square root of negative x? And if you take a look at this for the first time, again, these are horizontal stretches and compressions. And we haven't done horizontal stretches and compressions. Those are transformations that we've done for the very first time. This is the first time you've seen this transformation. So we've got to be able to perform this transformation at any given time. So if I take a look at this, what number should I plug in for x in order to get whatever I want for y? Again, the first number I should plug in is 0. Because when I do this, y equals the square root of negative 0, this is just going to be y equals the square root of 0, because there is no negative 0, and that's equal to 0. So when I plug in x equals 0, y is equal to 0. And then if I go to plug in a 1, so if I go to actually plug in a 1 over here for x, I can't do that, because when I plug in a 1 for x, that will be the square root of negative 1, which I cannot take. And then I can't plug in a 4 for x either, because if I plugged in a 4 for x, that would be the square root of negative 4. So obviously there's a problem here, so then you start asking yourself, you know what? I have to plug in negative values for x. Even though you can't take negative square roots, I know that if I plug in a negative 1, this is going to be y equals the square root of negative, and then x is negative 1, and a negative and a negative, or a minus and a minus, make a positive, so that's the square root of positive 1, which is 1. The next number that would plug in is negative 4, because the square root of negative, and then x is negative 4, a minus and a minus become a plus again, so that would be the square root of 4, and the square root of 4 is 2. And then obviously the last number that I would plug in is a negative 9, because I know when I plug in a negative 9, this will be the square root of negative, and then x is negative 9, a minus and a minus becomes a plus, and the square root of 9 is 3. Again, these are horizontal transformations in terms of your compressions and stretches, and you haven't seen this transformation never before, but you got to be able to apply this transformation. So even though we haven't seen this transformation, we've got our table of values here, and these are our table of values. I'd like you to take a moment and actually go to graph this table of values right now in the same set of axes with a different color of pen or something, and you'll end up seeing what the difference is between this graph and which is y equals, remember, the square root of negative x, as opposed to y equals the square root of x. And what you should find is that there is actually a reflection. So I'll just actually quickly draw this on this here. Your first graph should look something like this. I'll make it in blue. 0, 0, 1, 1, then 4, 2, and then 9, 3, and it looks something like this. And this is y equals the square root of x. And what I wanted you to do is figure out what the difference is between that and y equals the square root of negative x. And you'll see you'll actually get the point 0, 0, negative 1, 1, negative 4, 2, and negative 9, 3. And y in a different color of pen, this is y equals the square root of negative x. So I apologize about that. But what is the difference between these two? What did the negative do inside? We already know what happens when there's a half in front of the x. That's a horizontal stretch by a factor of 2 over 1. And we also know what happens when there's a 4 in front of the x. That's a horizontal compression by a factor of 1 over 4. But what happens when there's a negative in front of the x? As you can see, this changed, or this switched all your x values to negatives. So it is actually a reflection in the y-axis. Even though you are switching your x values to negative, this is a reflection on the y-axis. So it's a flip on the y-axis. So whenever you have a negative inside, that is a reflection on the y-axis. Again, we are taking into consideration just the horizontal stretches and compressions, and obviously the reflection in the y-axis. So we can understand that before we try to apply all the transformations together. We're going to now, in 1.8, we're going to actually start applying all the transformations. We're going to do, reflections in the x-axis, reflections in the y-axis, vertical stretches and compressions, and we're also going to do horizontal stretches and compressions, okay? And we're also going to do shifting left and right and shifting up and down. We have to do all sorts of transformations at any given time. So, again, now example 3 says, graph the two functions below plus the function of y equals absolute value of x on the same set of axes. So I want to graph y equals absolute value of x, absolute value of 2x, and absolute value of negative 2x. So let's go and do that. I'm just going to simply plug in these points of negative 2 all the way to 2. If I take the absolute value of negative 2, it's positive 2. Absolute value of negative 1 is positive 1. Absolute value of 0 is 0. Absolute value of 1 is 1. And absolute value of 2 is 2. Remember, absolute value means when you eliminate the absolute value sign, it is automatic. The number inside becomes positive after you've eliminated that. And of course, I can go and graph this, no problem, negative 2 to 2. And I will get the point 0, 0, negative 1, 1, negative 2, 2, 1, 1, and 2, 2. And this looks like something like this. Y equals the absolute value of x. And then, of course, I can go to graph this, and I'll graph this one in red. And if I graph this one here, this is, I want to graph the absolute value of 2x. So, of course, I'm going to bring this out over here so I can actually perform this operation here. Y equals the absolute value of 2 times, now I'm going to plug in x equals negative 2, and so this is y equals 2 times negative 2, which is, 2 times negative 2 in there, which is negative 4, and the absolute value of negative 4 is 4. So this is a 4. And then if I plug in a 1, a negative 1, I can plug in a negative 1. This is 2 times negative 1, which is negative 2. Absolute value of negative 2 is 2. If I plug in a 0, it's going to be 2 times 0 inside, and the absolute value of 0 is 0. If I plug in a 1, 2 times 1 is 2, absolute value of 2 is 2. And if I plug in a 2, 2 times 2 is 4, absolute value of 4 is 4. So if I go to graph this, I'm going to get 0, 0, I'm going to get negative 1, 2, I'm going to get 1, 2, I'm going to get negative 2, 4, and 2, 4. And it's going to look like this. Okay? This is a horizontal compression by a factor of a half. It got horizontally shrunk down by a factor of a half. Okay? Your K value is 2, but that's a horizontal compression by a factor of a half. Why is it horizontal, not vertical? It's horizontal because that 2 is inside of the function, inside of the absolute value being multiplied by my x. So this is y equals the absolute value of 2x. Okay? And then of course our last one here, as you can see, we already know what that negative sign does. Okay? But I'm going to try to do this all in one shot. We know what the negative sign does. The negative, switches our x values to negative, or it's going to be a reflection in the y-axis. Now what's pretty funny in this instant, also with the instance of a parabola, is that if you reflect an absolute value on the y-axis, whatever's on this side goes to that side, and this side goes to that side, you're going to end up with the exact same absolute value picture, because they already are symmetrical, perfectly symmetrical on the y-axis. So let's take a look at that one, and we'll do this one in green. Again, y equals the absolute value of negative 2x. So I'm going to have, if I plug in a negative 2, this will be negative 2 times negative 2. And negative 2 times negative 2 is positive 4. Absolute value of positive 4 is 4. And if I plug in a negative 1, I'm not going to do all these, but negative 2 times negative 1 is 1. Absolute value of 1 is 1. If I plug in a 0, you're going to get 0 in here. Absolute value of 0 is 0. If I plug in a 1, this will be negative 2 times 1, which is negative 2. Absolute value of that is 2. And if I plug in a 2, negative 2 times 2 is going to be negative 4, and the absolute value of that is positive 4. So if you go to graph that, you're going to end up with 0, 0. Okay? You'll end up with 1, 2, 2, 4. And you'll also end up with negative 1, 1, and negative 2, 4. So you're actually going to end up with the exact same graph as the absolute value of 2x, because it's a reflection on the y-axis. So even though you've reflected on the y-axis, it didn't change anything about this transformation. So again, it's very important that we know that the k value, which is inside of the function being multiplied by my x values, it is a new transformation. And this new transformation, it makes the thing either compress or stretch horizontally, or it's a reflection in the y-axis. You got to be able to apply this new transformation that we haven't seen before, and you got to be able to do it not only for these easy problems, but you got to be able to do it for the problems that involve all the transformations together. So as a recap, if your k value is a negative, it is a reflection on the y-axis. If your k value is a number bigger than 1, let's say for instance 2, it's going to be a horizontal compression by a factor of 1 over 2. And if your k value happens to be a third, then 1 over 3, then it's going to be a horizontal stretch by a factor of 3 over 1. And you'll be able to do all these transformations as long as you practice these questions and then apply them when we're doing all the transformations together.
Transformation style. Transformation style. Saw a bird standing at the origin, flipped it upside down. Then it's a reflection, spun it round. Right angle, that's rotation. That is rotation. Now sideways, 2 units to the right. Yeah, sideways, 3 units up. transformation style. Transformation style. Transformation style. Transformation style. Reflection, translation, rotation, transformation style. Reflection, translation, rotation, For a man trying very, very hard to dance, 50 upside down, then it's a reflection, spun it round, 360 degrees, that's a rotation. Now slide the guy, slide him 2 units to the right, yeah, slide the guy, 3 units up, I tell you, slide the guy, that's called the translation, a flip, a spin, a slide, now it's been otherwise taken. It's a reflection, and slide, that's a translation, if you spin, it's a rotation, transformation style. Transformation style. Transformation style. Transformation style. Reflection, translation, rotation, transformation style. Reflection, translation, rotation, reflection, translation, baby, rotation, reflection, translation, baby, rotation, what I say? Transformation style. Reflection, translation, rotation, transformation style. Reflection, translation, rotation, transformation style.